Good afternoon, my dear students. How are you? I'm fine. Do you learn yesterday's portion? Do you work out that one? That problems? Okay. Today portion variation in groups, atomic radius. So atomic radius variation in groups. So how many groups are present in our modern periodic table? Totally 18 groups are present in our modern periodic table. So from first group to 18 group come from top to bottom. Come from top to bottom. You can see this. If you moving from up to down, the electrons which are present in that elements are filled in different orbital or different shell. Okay, so here you can see in the period same shell electrons are filled, but in groups you can see they are filled in different shell. So see first one lithium 2s, next 3s, next one 4s, 5s, 6s, 7s. Here you can see the second group beryllium 2s, magnesium 3s, 4s, 5s, 6s, 7s. And here you see this one in third group 3D 4s, 4D 5s, 5D 6s, 6D 7s. Okay, so the number is increasing, atomic number is increasing from top to bottom of group, and also number of shells in that elements also it is increasing. Okay, so that means the electrons are filling in that element in different shell, not in the same shell. Okay, so they are not filling in the same orbital, they are filling in a different orbitals. Because of filling the electrons in more orbital, the size of atom is increasing. Size of atom is increasing. So the distance between the center of the atom and the outermost shell containing the valence electron is increases. So because of that, atomic radius is increases. It is because of filling electron into different shells, it is increasing the size of atom. So atomic radius is increasing with increasing atomic number in groups, only in groups, not in periods. Take page number 82 and look at this table 3.14. Variation of covalent radius of group 1 elements. So what are the elements present in group 1? First group lithium, sodium, potassium, rubidium and cesium. Look at the atomic number for this compound, these elements. It's increasing. Okay, atomic number is increasing with increasing covalent radius because of the addition of more cell to filling the electron. So lithium, it increase the atomic sodium is increasing atomic radius, and to have greater atomic radius than potassium, have greater atomic radius than sodium, and rubidium little more atomic radius greater, and cesium is greater atomic radius because of addition of electron in different shells. First periodic trend completed. Second periodic trend is Ionic radius. So Ionic radius is defined as the distance from the center of the nucleus of an ion up to which it exerts its influence on the electron cloud of the ion. From this Ionic radius method, you can calculate radius of ions. Radius of ions which is present in the crystals. Univalent crystals. Univalent crystals in the Ionic radius of uni and univalent crystals are measured or calculating by Pauling's method. We used here Pauling's method to measuring ionic radius of univalent crystals. Here, Pauling's assumed that ions present in a crystal lattice are perfect sphere. He assumed it is perfect spheres. Okay, perfect spheres. And he presented one equation to calculate at ionic radius of ions. D equal to R C plus R A minus. C is denoting as cation. So we have two type of ions. What are the ions we have? Cations and anions. A is denoting anions. What is the symbol of cation? Positive. What is the symbol of anions? Is negative. Okay. He derived one equation to find out ionic radius of one ion. D is equal to Rc plus Ra minus. So it is denoting that D is distance between two ions. Okay. Between center of the nucleus of cation. Center of the nucleus of cation and center of the nucleus of anion. Okay. So this distance is generally known as D. This is R, radius of cation. This is R, radius of anion. So adding this to radius, you will get the distance D. D is equal to Rc plus Ra minus. Pauling's assumed that radius of cation is inversely proportional to the effective nuclear charge of periphery of the ion. Radius of ion. Okay, radius of ion is inversely proportional with the effective nuclear charge. So effective nuclear charge of which ion? Cation. So we put here C plus 1 by Z EFF C plus. For writing the same one in the anion, Ra minus inversely proportional with effective nuclear charge of anion. Okay. So he derived here one equation. D is equal to Rc plus Ra minus. Rc is equal to Rc inversely proportional with 1 by EFF C plus Ra minus inversely proportional with effective nuclear charge A minus. Then write the effective nuclear charge formula. Effective nuclear charge is equal to Z minus S. Z is atomic number, S is screening constant. To solving this equation, we divide equation. For that you have to give the numbering to these equations. Equation 1. This is equation 2. This is equation 3. Divide equation 2 by 3 or C plus equal to C plus divided by R A minus equal to 1 by effective nuclear charge of cation divided by effective nuclear charge of anion. Then Rc plus divided by Ra minus equal to effective nuclear charge of anion divided by effective nuclear charge of cation. We consider this is equation 4. Okay, let's calculate the ionic radius of sodium fluoride. What is cation? Sodium. Fluorine is anion. So you can write 2 ions, sodium plus and F minus. Here they are given the distance value already given is equal to 231 picometer. 231 picometer. So from D you can find out the ionic radius. R C plus R A minus. How to write this equation for sodium fluoride? Which one is cation? Sodium, anion, fluorine. So write distance D equal to radius of Na plus radius of F minus. Okay, we consider this is equation 5. Then from there you can write R, because what is D value? 231 picometer. Substitute this value in equation 5. R Na plus R F minus equal to 231 picometer. We consider this is equation 6. Then apply equation number 4. Write equation number 4. What is equation number 4? R C plus divided by R A minus equal to effective nuclear charge of A minus divided by effective nuclear charge of C plus. Write that equation for sodium fluoride. R, what is C plus? Na plus. So write here Na plus divided by R A minus. What is A minus? Fluorine. So F minus equal to effective nuclear charge. Effective nuclear charge of A minus. What is A minus? Fluorine. F minus. Then effective nuclear charge of C plus. What is C plus? Sodium. Na plus. Okay. Then write effective nuclear charge equation. To find out the effective nuclear charge, Z minus S. This is the equation for finding out effective nuclear charge. Z is atomic number and S is screening constant. So screening constant is already given for sodium and fluorine. Sodium plus screening constant 4.15. F minus screening constant 4.15. Okay, they are already given this data. So apply this values in this effective nuclear charge equation. What will you get? Effective nuclear charge equal to, what is the atomic number of fluorine? What is the atomic number of fluorine? Is 9. So 9 minus is at 9. So write 9 minus, what is the S value for fluorine? 4.15. So write here 4.15. Okay, so what is, say the answer? 4.85. This value is the effective nuclear charge of anion or fluorine. Like the same, calculate the effective nuclear charge for cation. Effective nuclear charge of cation, sodium plus is equal to Z minus S. What is Z value? Is 11. Atomic number 11 minus S value. What is the S value? 4.15. 4.15. Then subtract this 2. You will get the value 6.85. This is the value of effective nuclear charge of sodium plus. Then apply these values in the equation number 4. So R Na plus divided by R F minus equal to effective nuclear charge of F minus, right? So what is effective nuclear charge of F minus? It's 4.85. So apply this value in that equation. 4.85 divided by, what is the effective nuclear charge of sodium? 6.85. 6.85. And you will get the value is 0.71. This is the value. So from there, R Na plus divided by R F minus is equal to 0.71. Then take this R F minus into the next side, then right side. So R Na plus equal to 0.71 into R F minus. Okay. Then substitute this R Na plus value in equation number 5. What is equation number 5? D is equal to R Na plus R F minus. So substitute the value of R Na plus into D, equation number 5. Okay. Substitute R Na plus into equation number 5. Okay. D is equal to 231 picometer. R Na plus equal to 0.71 into R F minus. So substitute this in this equation. What is D value? 231 picometer. 0.71 Okay, so substitute this value. R Na plus is equal to 0.71 R F minus. So substitute this value in the place of R Na plus R F minus is equal to D, 231 picometer. Then find out R F minus value. So 1 RF plus 0.71 RF. Okay, add this both. You will get 1.71 RF minus equal to 231 picometer. find out RF value from this equation. RF minus equal to 231 divided by 1.71. And you will get the value of this calculation 135.1 picometer. Then we find out only RF value. We have to find out RNA plus value. How to find out? Substitute this equation, this RF minus equation, into equation number 6. What is equation number 6? RNA plus RF minus equal to 231 picometer. Then substitute this value in this equation. RNA plus, what is RF value? 135.1 picometer equal to 231 picometer. So RNA plus equal to 95.9 picometer. So the radius of ions sodium plus and F minus is calculated by Pauling's method by using given experimental data, RNA plus value and RF minus value. Next topic, third periodic trends in atomic modern periodic table is ionization energy. Third one. So ionization energy is a minimum energy. It's the minimum energy. So minimum amount of energy required to remove electron from the orbital. So this removed electron, it is a loosely bound electron in one orbital. Okay, loosely bound electron in one orbital. So ionization energy, the definition of ionization energy is the minimum amount of energy required to remove electron from the valence shell of to remove the most loosely bound electron from the valence shell of the isolated neutral gaseous atom. Okay, gaseous atom in its ground state. So here we required some energy to remove one electron from a particular gaseous atom. So it should be in the ground state. That electron, which electron is removing, it is a loosely bound electron in a outermost orbital or the valence orbital. Okay. This ionization energy is generally expressing here by the unit kilojoule mole power -1, or you can give the another one electron volts. Okay, so we have two units to define this ionization energy, kilojoule mole power -1 and the electron volts. Take one gaseous atom. G is gaseous, this M is one atom. It requires some energy. It is minimum amount of energy required to remove electron, loosely bound electron from a orbital. So here this is first energy. So you put here first energy, ground state 1, first energy. Okay, first energy 1. Okay, this is first. And it gives removal of one electron. So one electron is removing from M gaseous atom. So one electron is removed. One electron. This symbol is denoting, E minus is denoting, this is electron. So how many number of electron is removed here? One electron is removed from this M gaseous atom. So this M is become M plus. It's become M plus. How it's become M plus? Because it's removed, it's lose one electron. It's lost one electron from that gaseous atom. So because of loss of electron, we have to mention here is positive or cation. You have to mention. So if any compound is denote like this, then it is the meaning of one electron. It's lost one electron. If the compound is denote like this Na2 plus, then there is 2 electron lost. Okay, so from that equation you have to understand one gaseous atom is required some minimum energy to remove one electron, loosely bound electron from that atom. So now this compound is become M plus. It's denoting it's lost one electron because of ionization energy. This ionization E energy in the first energy. So it is 1. Okay. Take that same gaseous atom which is the product of first equation M plus. We treat this M plus with some small amount of energy or minimum energy, that is ionization energy. So we given here energy in second time, so we put here it's 2, second ionization energy. Now this unipositive, this one element unipositive, okay. So this one element contain only one cation. So this unipositive element is require some energy, ionization energy, the minimum amount of energy to remove one more electron from this M plus. So what is the result of this equation? It is M, already it's contain one cation, that means unipositive. So because of this second ionization energy, it's lost one more electron, so we mention here it is M2 plus. Why we mention here it is M2 plus? Because already it contain one cation. Because of the second ionization energy or the successive energy, it's lost one more electron, so it's become M2 plus plus 1 electron, because this is lost. Okay, this 1 electron is removed from this unipositive compound, unipositive gaseous atom. This energy is known as successive energy. Successive ionization energy. Successive ionization energy. So the minimum amount of energy is required to remove an electron from a unipositive cation. From a unipositive cation is called second ionization energy or successive energy. Okay. So the like the way we remove the electron from the gaseous atom with applying the minimum amount of energy or the ionization energy, that ionization energy 3, ionization energy 4. Likewise, they all known as successive ionization energy. Successive ionization energy. Because of this ionization energy, electrons are removed, but the positive is present in the nucleus, or the nuclear charge is not decreasing, it's not decreasing, okay, because only removal of electron is going on because of the ionization energy. It's not removing the proton from the nucleus. Therefore, the effective nuclear charge of the cation is higher than the corresponding neutral atom. Okay, so you take that one neutral atom, this is one neutral atom and this is one cation. Okay, now from this neutral atom we didn't remove any electron, but the cation we remove one electron. So one electron is removed, so the number of electron is decreased, but the number of electron is same. It is same in this neutral atom. Now count the proton number in the neutral atom and proton number in the cation. Here proton number is same with the electron number, but here it is not same with the electron number because one electron is removed. So the nuclear charge of cation, nuclear charge of cation is greater than the neutral atom. So the successive ionization energy is always in the increasing order. So they are given the order like ionization energy 1 is less than ionization energy 2. Then it is less than ionization energy 3. Okay, this is the series. Okay, so you can write ionization energy 4, etc. So this is successive ionization energy. I hope you all understand this concept. Thank you, students.